All right, I think.
Can you guys hear me?
Yes.
Yeah. All right, cool. Welcome. Thank you so much for coming out tonight. It's such a pleasure to see so many people in the room interested in neuroscience, interested in art, interested in research. My name is Jen. I'm the president of the NEURO Club for the 2013-2014 academic year. For those of you who don't know what NEURO is, we are the Neuroscience Education University Research and Outreach Club. We were formed in fall 2011 and have since then been doing activities related to undergraduate enrichment and graduate enrichment in terms of bringing lectures like tonight and opening various options for students to do research in neuroscience labs. We do educational outreach in local schools, and we have big community events like the Brain Awareness Week we had last quarter and a brain dissection coming up this spring. We're also working on creating a neuroscience major in the college and other outreach opportunities, as well as partnerships with other neuroscience-related organizations at the University of Chicago and the Chicago greater area. And it is our pleasure tonight to welcome Margaret Livingstone.
Hi everyone, my name is Christian. I'm the public relations head for NEURO. So a couple logistics before we start. If you need to get up during your talk, if you could go towards your left. We're just kind of recording the talk on the right side. And also, everybody has reading glasses. If you don't, if you want to raise your hand and one of our NEURO executive board members will find you and give you a pair. Dr. Livingstone will be during your talk. Without further ado, I want to introduce Dr. Margaret Livingstone. She's a professor of neurobiology at Harvard Medical School. In her lab, she studied dyslexia, learning, hormones, and what you guys are probably here to see, learn about art and vision. So she's, a lot of her research has informed how we perceive art and what makes art so appealing. For example, the Mona Lisa, why is her smile really elusive? But I'll have her introduce herself more in detail. Without further ado,
So I am a visual neurophysiologist, which means that I study how we see by recording from neurons throughout the visual system. But I acknowledge that artists also do experiments on how we see, and many works of art reveal important things about the way our perception works. Now, I know that a lot of works of art reveal important things about human culture and human psychology, and they're important, but I'm not going to talk about them because I work on low-level vision. I'm going to talk about works of art that reveal important things about how we see. Artists have known for a really long time that you can represent the world or an image or a scene with a line drawing. And it's so deeply ingrained, so intuitive, that you have to think for a minute to realize that the world is not full of lines. It's full of contours and discontinuities, yet we accept a line as a representation of a contour. And the reason that we do, I've lost that pointer that I had. What did I do with it? Who knows where my pointer is? Oh, I found it. We're okay. And the reason that lines work so well to represent contours is because of the way your visual system, practically any visual system, deals with light. Steve Kupler discovered that if you shine a spot of light on the retina, you get a barrage of signals from a retinal ganglion cell. This is when the light was on. What he discovered that was really peculiar was that if he shined a bigger spot of light on the retina, more light, he got, paradoxically, a smaller response. And Steve deduced that that's because retinal ganglion cells are excited by light in one part of the visual field, but inhibited by light in the immediate surround. So when he shined an annulus of light on the retina, he got a suppression of firing. He called this center surround antagonism, or lateral inhibition, and your visual system starts with lateral inhibition. In case you don't believe me that your visual system is full of center surround cells, do you see the little gray spots everywhere where you're not looking? And don't worry about the fact that it's everywhere you're not looking, because that's postgraduate. You see the little gray spots because center surround cells at the intersections have more white in their inhibitory surround. So they're more inhibited or less active than center surround cells along here. So you see the little gray spots. The surround has to have one extra synapse in order to manifest itself. And so there's a little tiny temporal delay between the center and the surround, which makes it sort of scintillate here. That's a static image. So if you get anything from my talk, I hope you get the idea that vision is information processing, not image transmission. It doesn't do you any good to send a high-resolution image to the back of your brain because there is nobody up there to look at an image. All you have up there are neurons, and all they can do is fire or not fire. So visual computations are simple. All you have is neurons. All they can do is fire or not fire. They're local because neurons are little tiny things, and they're often opponent because neurons can either excite each other or inhibit each other. So why is center surround information processing? If you had an image like this, white on one side, dark on the other, center surround cells over here are not active, center surround cells over here are inhibited. It's only center surround cells at the discontinuity where there's an imbalance between the center and the surround where you get a signal. So center surround cells turn a contour into a line drawing. And you know this is efficient if you've ever tried to save an image on your computer. If you save this as a TIFF file, it would be several megabytes because you have to save the value of every pixel in the image. But if you compress it to a JPEG file, it's much smaller because JPEG does what your visual system does. It only records where something changes, where the discontinuity is and what the sign of contrast is across the border. This is just to remind me how efficient a line drawing can be in conveying information, but it also allows me to point something out. What color are the lines? This is not hard, come on, black. What color is this screen? White. So you know that the amount of light coming to your eye from those black lines is the same as the amount of light coming to your eye from this white screen, right? Because that projector can't project blackness. All it can do is project white. Your visual system does not care how much light there is at any point in the visual scene. It cares about contrast. It cares about where information is happening. So you're, oh, all right, it's good. I think it's going to get a little less complicated in a minute. Let's try this one. No, this one. So your visual system maps visual space first onto your retina and then onto your visual cortex. So when I talk about local computations, what I mean is local on cortex, so nearby neurons in cortex. And nearby neurons in cortex deal with the same part of the visual field. So as you march across the visual cortex, you march across the visual field. All neurons that project long distances in cortex are excitatory, bar none. All inhibitory neurons are local. So inhibition, or surround inhibition, is always local in cortex. So as I mentioned, in cortex you map across visual space. So if surround suppression is local, that means it's local in visual space, which means that you can have these local surround effects, which I already showed you that Steve Kupler discovered, but here's an illustration of it. All of these discs are exactly the same gray. Now I know they are because I made this. But this one looks much lighter than this one because this is surrounded by light and this is surrounded by dark. So luminance exhibits local opponency. Contrast exhibits local opponency. These checks are identical to these, but these look higher contrast than these because these are surrounded by high contrast and these by low. Orientation is locally opponent. Those center stripes are vertical, but they look off vertical because they're surrounded by a different orientation. Motion is locally opponent. That red dot is moving vertically, but it looks like it's moving off vertically because of the surround motion. Color is locally opponent. Those rings are all identical, and I know they are because I made this, but like you, I see this one is more yellow or less blue, and this one is more blue or less yellow because of the surround opponency in color. And here's a little illusion based on that. I want you for just a second to look at that little black dot, and I want you to keep in mind that what you're looking at is white letters, and now because of surround opponency in color, you are going to see a yellow after effect from white letters. Of course artists know this. Monet painted his shadows blue with little yellow surrounds. So vision is information processing. The computations are simple and local. I want to find a different light level. Let's see what I can do with this. Try that for a while. So when you look out on the world, it looks vividly three-dimensional. So even something as seemingly complicated and global as depth perception is calculated by simple local neuronal computation. So you look out on this world and it looks vividly three-dimensional, right? You have to agree with me. Yes, the world looks three-dimensional. Now I know the world is three-dimensional, I'm not denying that, but the fact that you see it as three-dimensional is done with two flat retinal images. That's all you start with, is two flat retinal images, and from these two flat retinal images you compute distance and depth. You don't have a sonar system. You have to use information to compute distance and depth. And you use things like relative motion, so if you move back and forth, things that are near move more than things that are far away. Shading, perspective, occlusion, and stereopsis, which I'll talk about at the end. You use all these cues to compute distance and depth. So there are computer graphics people who will sell you for a remarkably large amount of money a program called a ray tracing program that will calculate how light would bounce off a three-dimensional object and produce a flat image that you can take a picture of. But you don't need to take into account all these laws of physics because it's pretty well guaranteed that the laws of physics are going to be obeyed. You don't have to go around checking that the laws of physics are being obeyed. And so these computations are local. They start early in your visual system where everything is mapped across visual space. And artists have ignored the laws of physics for centuries. So when artists first figured out about using shadows to create a sense of three-dimensionality, often the shadows went in orthogonal directions. Nobody cared. Now I want another different light level for this one. Here's a vase of flowers where the shadow is going towards the sun. Nobody cares. This is Canaletto's painting of the Piazza San Marco. And in this half of the painting, the shadows are going in this direction, and in this half of the painting, the shadows are going in this direction. This is at the Harvard Art Museum, and I was being interviewed, and I pointed this out, and one of the curators came running over and said, "That's because the light is coming over here and reflecting off the stone." I went to the Piazza San Marco, and there is no time of day during which this building is full of windows. It does not reflect light. The shadows do not go in two different directions in the Piazza San Marco. In this Edward Hopper painting, this thing isn't casting a shadow where you'd think it would. Here's a manger that you see from the top on this side and from below on this side. No one cares. Now, I don't think that halos should necessarily obey the laws of physics, but I think that they should at least be internally consistent in whether they occlude things or not. I think Magritte was playing with occlusion in this painting. If you find any painting that's got a mirror in it, I guarantee you it is not obeying the laws of physics. If this lady were looking at herself in the mirror, which is what the narrative of the painting seems to imply, you, the viewer, would not see her face, right? And even Vermeer painted this nice shiny brass bowl, which seems to be shiny because it's reflecting the tablecloth. But if you look carefully, you will see that what's being reflected in the bowl has nothing to do with the tablecloth underneath it. Nobody cares. It's past my bedtime, so I have to keep turning the lights on. So another thing that artists figured out that us neuroscientists are just now starting to understand is that color and luminance do two very different things for you. And don't worry, I'm going to say what luminance is in a second. He said colors are only symbols. Reality is to be found in luminance alone. We have three cones, short, middle, and long. We see color by comparing or using opponency between pairs of cones. We see luminance by simply summing the activity in our three cones. So if you have, and if there are any artists in the audience, the word you want is value. I'll try to say that every once in a while, just for variety. Usually a color contrast border also carries a luminance contrast, but you can have color contrasts that carry no luminance contrast. And when you do, as Joseph Albers pointed out, very peculiar things happen. This is Monet's Impression Sunrise. It's the painting after which the Impressionist movement got its name. You have to, it doesn't come out as shimmery as it should. The sun in Impression Sunrise, which is at the Marmottan in Paris, you have to go, I'm sorry, It's impossible to reproduce this. It shimmers. It looks sort of hot and cold and bright and dark at the same time, and it's absolutely brilliant. And you would think that the sun would have a higher luminance than the background. It's a source of light, right? But I once got a small grant from Harvard to go to Paris and measure the luminance of the sun in impression sunrise. And surprisingly, it is, well, not surprisingly to me, frankly, it is exactly the same luminance as the gray sky background. And I think it's because it has no luminance contrast that it has this peculiar, shimmery, brilliant quality. And that is because your visual system and the primate visual system in general, once it leaves the retina, gets to primary visual cortex, it splits into these two major processing pathways. And we know what these different processing pathways do because of what happens to people who get lesions in different parts of their visual system. So people who get lesions in this ventral or temporal lobe part of their visual system acquire what are called agnosias. They can see objects, they can copy objects accurately, but they just can't recognize them. They don't know what they are. You can lose surprisingly specific categories of objects like faces, which is called prosopagnosia. So we call this the what system because it's for recognizing objects. This part of our visual system is a primate add-on to the basic mammalian, evolutionarily older visual system, which is more like what our dorsal stream is like. So our dorsal stream carries information about motion, depth, figure ground segregation, and spatial organization. So some people call it the where system because that's kind of where-like information. Some people call it the how system because they think it's for how you interact with your environment. And it does everything that a self-respecting visual system should do. It allows an animal to navigate through its environment, to avoid obstacles, to recognize predator and prey. But what this part of our visual system can't do is what we as primates are good at, which is recognizing objects by their fine features and see color. So here are some drawings made by people with lesions in their wear system. These people were asked to draw a bicycle, a cross, and a clock. So you can see they get all the bits right, but the bits are in the wrong spatial organization, kind of like a cubist drawing. Not to say that Picasso had a parietal lobe lesion, but rather that he cottoned on to how independent where something is and what something is can be. So what's important for what I want to talk about now is that this evolutionarily old part of your visual system is, like other mammals, essentially colorblind. So if you had a red spot on a green background, and you took a black and white photograph of it, or looked at it with your wear system, you'd see a gray spot on a gray background. And you could imagine tailoring the brightness of the red in such a way that you would have identical grays. That's equal luminance or equal value. And weird things happen at equal value. So for me, this one has kind of got that weird shimmery quality, and maybe that one. Weird things happen when a whole part of your visual system can't see something. So now I'm going to try to convince you that your ability to see depth, spatial organization, and figure ground segregation are carried by a colorblind part of your visual system. And of course I have to fiddle with the lights again. And now I'm going to show you a rotating sphere. Did it start? No. There it is. Okay. No, that's the other one. This one. There. That's a sphere, right? Okay. So I'm going to make the red dots brighter than the green. You can see why I have to turn the lights on. So this should look three-dimensional, right? It's not. Okay, it's flat. But it looks three-dimensional, and don't worry, it's going to flip direction at some point, and that, again, that's postgraduate. People love to study it. And it looks three-dimensional whether the red is brighter than the green or darker than the green. But if I go through equal value, equal luminance, I hope I can make it flat and squishy. And then three-dimensional again, and let's go through flat and squishy. So that's steps from relative motion, going away at equal luminance. So you can tell that there's some information about depth, shading, and stuff like that in this image. But I hope I can make it look more three-dimensional to you if you close one eye and look through the red lens of the stereo glasses. See, I knew they were going to use that. I bet you didn't know we were going to do this with them. Does it look more three-dimensional when you introduce a luminance contrast by blocking the blue? You don't have glasses. Help, we need glasses. Sorry. You'll need them again and again and again. Thank you. Some of them are in rubber bands. Ah, good. Okay, thank you. Okay, let these people get to see it. I'll have a little drink of water here. So close one eye, look through the red lens, see if it doesn't look more three-dimensional. Okay, now everybody put the glasses down. Hey, good, good. Now, before you put the glasses up again, look at this image. Think about whether you see all the depth from perspective, depth from shading. Can you even figure out the figure, the ground, what's going on? And then close one eye and look through the red lens and see if this thing doesn't look more three-dimensional and make more sense as an image. Okay, glasses down. Monet painted a whole bunch of versions of this cathedral in Rouen, and because it's a beige stone building, it's all about the way light bounces off three-dimensional surfaces, like the rose window in the doorway, and the information is all there, and the luminance alone. But in some of them, it looks flat and shimmery, and that's because he uses pairs of colors that are close to equal luminance, equal value, and he gets this flat, shimmery quality. This one's at the MFA in Boston. I think Lichtenstein was playing with this in this version of the Rouen Cathedral, and I bet you can't even tell that it's a Rouen Cathedral until you close one eye and look through the red lens. There it is. Andy Warhol was playing with this in this poster that he made of the Brooklyn Bridge. The bottom half of the poster uses a pair of colors that are close to equal value, and the top half, exactly the same image, but using colors that have a luminance contrast, looks more three-dimensional. And Andy Warhol, I actually don't know if this was Andy Warhol, but you can't even figure out who this is, right? But if you were my age, you would recognize Gracie Slick. So if your ability to see color is carried by a colorblind part of your visual system, then it doesn't matter what the color is as long as the luminance is right to give you a sense of three-dimensionality. Of course, a number of artists figured this out and were playing with it. This is André Durand's portrait of Matisse. If you knew Matisse, you'd recognize him right away from the shape of his face. Even though the colors are weird, the luminance is exactly right to portray the subtle shape of his face. And of course, Matisse's Lady in a Hat, when it first came out, everybody was all upset about it because of the colors, the weird colors that he used. But as Picasso said, he was using colors symbolically. The reality is there in the luminance alone. So now I want to try to convince you that your ability to see motion is carried by a colorblind part of your visual system. And this time I'm going to use the right one. So I'm just going to slow this down. I forget which button slows it down. Probably going to take it off. Oh, I did it. Okay, so you can cheat if you want and look at the center and you'll know that these things are always moving at exactly the same speed. But what I'd rather you did is look at the right-hand edge of the moving black and white stripes. And if the green stripes are brighter than the red, both sets of stripes seem to be moving at the same speed. If the green is darker than the red, both sets of stripes seem to be moving at the same speed. But if I go through equal luminance and make this a suboptimal stimulus to your motion system, I hope you see the stripes on the left is moving more slowly than the stripes on the right. Of course, you can cheat and see that they're not. They are. If your ability to see that something is moving is colorblind, your ability to see that something is not moving is also colorblind. So art historians carry on quite a bit about how much motion there is in many of Monet's paintings. I think he did this by using equal value, equal luminant colors. So the poppies are almost exactly the same luminance as the background. Your what system can see them, but your where system can't tell where they are. So their position can move. They can seem to sway in the breeze. Now, I don't know if Monet knew that he was achieving a sense of motion, though the art historians often say he did, but I know Mondrian knew he did because the title of this is Broadway Boogie Woogie. The original's at the moment in New York. It's about this big across, and it's absolutely nauseating how it jumps around. And I think it jumps around because your what system can see the yellow checks, but your where system can't, so their position is indeterminate. Advertisers do this all the time. You open Wired magazine, you can find a headline or an ad that's one color text against an equal value other color, and it's very unpleasant to look at, but it also catches your attention. And catching your attention is something that advertisers like to do. So I hope I've convinced you that your ability to see motion, depth, spatial organization, and figure ground segregation are carried by a colorblind part of your visual system. Now I want to try to convince you that your ability to see color is low resolution. Of course, artists know this. Watercolor artists can put a color, an outline on a canvas or a piece of paper, and then apply a color quite loosely to the shape, and yet your visual system accepts that shape as being assigned to that contour and doesn't get freaked out that the artist didn't color inside the lines. Here's an illusion based on that. I hope you see the donut as yellower than the whole or the background. Good, okay. It's not. I know it's not. I made this. The donut is exactly the same white as the whole or the background. These are just two lines, a yellow line inside a purple line. But because your color resolution is low, the yellow color spread, I know, I see this too, it's astonishing, but I know that I made it, okay? I know this is exactly the same color as this. But I agree, it doesn't look the same. The color spreads until it hits a border. So now I'm going to use some after images to generate some blurry colors so that you can watch your color spreading until it hits a border. What I want you to do is look right at that little intersection of these three shapes, and then you're going to see a homogeneous gray background and get an after image, okay? Now let's do it again. Look at the intersection and see if you got a color after image. This is an achromatic image. Now some of you are saying, well, of course it was better the second time you did it twice, right? That's not the reason. Look at the intersection, evaluate the after image. Look at the intersection, evaluate the after image. Now here's another version. Look at the intersection and see if the color fills a completely different shape. And now look at the intersection and watch the color flow up the hole. So I wrote a book about vision and art, and while I was writing this book, my editor told me that it was obvious I knew a lot about vision, which is true. But he said it was also obvious I knew nothing about art history, which is also true. And so he told me I had to read an art history book. So I did. I read Gombrich, which is a very good art history book, but I only got to the Renaissance because I got stuck at the Mona Lisa. Gombrich says he wants you to look at this painting as if you've never seen it before, as if you haven't seen it in ads or with mustaches or on postcards or whatever. There is a reason why this is such a phenomenally popular painting. Her expression changes as if she is alive. And I thought, oh my goodness, maybe he's right. I look at it a little while and I thought, no, maybe he's right. See if you don't see what I see. Look at her eyes and think about her mouth. Now you have to be aware of where you're looking, okay? As a visual physiologist, this is really easy for me, but apparently a lot of people have trouble doing this. Look at her eyes, think about her mouth. Don't cover up her mouth, just look at her eyes, think about her mouth, and then look directly at her mouth. And look back and forth between her eyes and her mouth and see if you don't notice the same thing I did. See if you don't think she smiles more when you're looking at her eyes than when you're looking right at her mouth. And it's her mouth that's smiling, not her eyes, right? So Gombrich says that this happens because Leonardo used sfumato. He made her blurry. And that makes her smile ambiguous. And I thought, well, if it's ambiguous, that should depend on your state of mind, not where you're looking. Where you're looking is really low level. And of course, as a visual physiologist, I know that our acuity falls off dramatically from our center of gaze. So if you look at that dot, all these letters are equally readable. That's how much your acuity falls off from your center of gaze. Your central vision is really good at seeing little, tiny, detailed things. That's why you have to move your eyes when you read. Your peripheral vision is not just a bad version of your central vision. Your peripheral vision is actually better at seeing big, blurry things. For those of you a little bit more technical in the audience, the central visual field is for high spatial frequencies, and peripheral visual field is better at low spatial frequencies. But if you don't understand what I just said, don't worry, okay? It helps some people. If you filter the Mona Lisa in such a way that you see what she would look like to your peripheral vision, as opposed to your central vision, if you could see the whole thing with your central vision all at once, which of course you can't, you can see that she's grinning from ear to ear in your peripheral vision, but she's hardly smiling at all in your central vision. That is, her smile is all there in the blurry parts, the low spatial frequencies. Now you move your eyes constantly. You move your eyes 2 or 3 times a second. You have to. If you don't, your vision fades because your visual system depends on temporal discontinuities as much as it does on spatial discontinuities. So as you move your eyes around, her expression changes. 500 years ago, a dynamic quality in a static image was something really special. It also gives her a kind of a coy quality. You notice when you're looking at the background that she's smiling, and then you look really fast at her mouth to try to catch her, and she stops. I think the same thing holds for the pointillist. You have a fabulous one here at the Art Institute. The pointillists get a vibrant, brilliant color. They themselves thought that their brilliant color came about because of what they call additive, what is additive color mixing. That is little dabs of paint that mix their reflectances, as opposed to if you mix colors together on a canvas, you mix the absorbances. That's subtractive color mixing. But I don't think there's anything special about additive color mixing because magazine illustrations are just little dots of ink, right? There's nothing special about the color in a magazine illustration. I think the vibrancy in pointillist paintings comes about because your center of vision sees the dots, your peripheral vision sees the river, the tree, the rowboat. So as you move your eyes around, what you see changes. That's dynamic, that's vibrant. Like in this one, if you look at this reflection, you see dots. If you look at the rock, the reflection looks like stripes. And if you look at the house over here, it looks like a solid. So it changes depending on where you're looking, the way water changes. A reflection in water. Sometimes it's dots, sometimes it's a line. So it lends a sense of vitality to an image. Chuck Close, of course, does this with these huge tiles that he makes. With your central vision, you see the tile. With your peripheral vision, you see Chuck Close. Photo mosaics, which were Robert Silver's homework assignment for a course he was taking in the Media Lab. He invented them. Your central vision sees baseball cards. Your peripheral vision sees Babe Ruth. So now I want to talk about how we recognize objects with our temporal lobe. So vision is really difficult. It's surprisingly difficult, given how good we are at it. So you have to, it's hard to realize how good we are at it, except to recognize that our government has spent billions of dollars trying to make a car that can drive without a driver and not fall off the road. So we are so good at vision, it's hard to realize how difficult it is. But we're good at recognizing things. And we're particularly good at recognizing faces. You're detecting faces in 1/10 of a second. You're not only detecting them, but you're recognizing particular individuals. And you can do this whether these are caricatures or cartoons or degraded or occluded, and you can do this better than any computer program. We are very good at processing faces. We have particular parts of our temporal lobe that are dedicated to processing faces. We know that because people can have lesions in their temporal lobe and lose the ability to recognize faces and still recognize all other categories of objects. And using functional MRI, you can visualize these parts of our brain. But again, artists are ahead of us in understanding how it is we process faces because artists have long recognized that caricatures are much easier to recognize than veridical line drawings. Caricatures look less like an individual than a veridical line drawing, and yet they evoke an identity much better than a line drawing. Why do caricatures work so well? What is it about caricatures? Well, we've recorded from face cells, so macaque monkeys also have regions in their temporal lobe that are dedicated to processing faces. And monkeys, like us, use faces to recognize conspecifics and to convey important social information. So we recorded from cells in face patches in macaque monkeys. First of all, if you put an electrode in a face patch, you find it chock full of cells that respond to faces. And face cells in macaque monkeys will respond to people faces, monkey faces, and cartoon faces. Anything you'd call a face cell will respond to. So we use the fact that they respond to cartoon faces to probe how do face cells recognize faces, or how do we use face cells to recognize faces? And so we varied everything we could think of in 20-parameter face space. The shape of the face, the shape of the eyes, the shape of the mouth, the nose, everything we could think of. And we varied these parameters simultaneously and recorded from face cells. And we tried to go kind of extreme in our parameters because actually what we thought we were trying to do was map face space. So you can see that we got outside of what you'd consider reasonable primate face space. And here, this is the only science you're going to get. If you came for the science, this is it. These are 3 face cells, 1 in each row, and each column is 1 parameter. So this little graph means that this face cell did not care about eyebrow width. This cell cared about eyebrow slant, these 2 didn't, and so on. So a cell cares about something if the cell responds more at one part of the parameter than another. You can see each face cell cared about a few parameters. So the first answer is face cells don't code individual faces. If it did, we'd never have found anything. Instead, face cells care about parameters, about variables that describe a face. And each face cell cares about a few of them. So you have overlapping constellations of parameters in a population of face cells. So that probably is how you code face. But the other thing we noticed, and it was inescapable, you might think that if you had a face cell, if you wanted to have face cells code inner eye distance, you might want one for big, one for medium small, and so on, and one for really small inner eye distances. Or you could have one cell that cared about really big inner eye distances and was inhibited by small, and then another cell that liked really small inner eye distances and was inhibited by big. This is more efficient because you get everything in between for free by the ratio of these 2 cells. And indeed, that's exactly what we saw when we recorded from face cells. If a cell cared about some parameter, it tended to be peak at one extreme and be inhibited at the other. That is ramp-shaped tuning. Ramp-shaped tuning is consistent with caricature. What's a caricature? You take a face, you figure out how it differs from the average face, and you exaggerate the difference. So that's what face cells do. They tell you, how does this face differ from the average face? Face cells are taking a caricature. As I said, artists were way ahead of us in figuring this out. These are portraits that Picasso made, and like many portraits that Picasso made, they're a little weird, but I put them next to a photograph of the person they're a portrait of. They're all caricatures, aren't they? So this is Picasso, Gertrude Stein, Igor Stravinsky, wife, girlfriend, mother-in-law, art dealer. But they're all caricatures. He's figured out what's unique about each of these individuals and exaggerated it. So ramp-shaped tuning also tells us that face processing involves within-category comparisons. You can't say how a face differs from the average face unless you're comparing faces. So it means that face processing, like everything I told you about at the beginning, is local and opponent. What do I mean by that? Well, I told you when you march across early visual cortex, you march across visual space. When you march across infratemporal cortex, you march across object categories. So first you'll hit a bunch of cells that care about faces, and then you'll hit a bunch of cells that care about body parts, and then maybe a bunch of cells that care about places. So nearby cells in infratemporal cortex code the same object category, which means, because inhibition is local, that you can have within category comparison in faces. So now I want you to look at these numbers while I talk on about this, okay? And the reason I want you to look at these little numbers is because I want you to get a face identity after effect, but I don't want it to be a stupid little low-level retinal after effect. I want it to be a high-level face identity after effect. So now I am going to show you 2 identical morphs, and I hope you got a face identity after effect. So vision is information processing, not image transmission. You can see this manifest in the work of many artists. You can see this manifest in the art of children. If you ask a 3-year-old child to draw a person, you will get a face on legs. Any 3-year-old child. The child is telling you what's important about a person's identity. This is the information the child has extracted, the information that's important about the identity of a person, their face. This is a drawing a child made of her pregnant mother. A face on legs, inside, a face on legs. Matisse explicitly said, I don't paint things, I paint the difference between things. So I get invited to sometimes kind of odd places, and I got invited to the Museum of Art and Design in New York, which isn't inherently odd, but it was odd because they were having an exhibition of dioramas. And I thought, I don't want to see an exhibition about dioramas. My children are no longer in middle school. But I went, and I was really glad I did, because they had dioramas that were like little tiny scenes of urban decay or mass destruction or ordinary suburbia, something like, and yet they were exquisite. And if these things had been the right size, they would be far from exquisite. And I started thinking, why are these things so interesting to look at? You ask the artists, and they say, I'm trying to get you to look at it differently. Now, I have learned over the years that artists say stuff sometimes that it doesn't resonate with me as a scientist necessarily, but if you think about it, it often turns out they're saying something profound. And I think this time they were. They were trying to get us to look at something differently. And I had to think, what are they doing? And then I thought, because I'm working in inferotemporal cortex, well, inferotemporal cortex is full of these modules for special object categories. And we know this because of the kinds of agnosias people can get from lesions in their temporal lobe. People can get agnosias for small manipulable objects, places, spaces, I told you that. Also things like text and body parts. That means that we have modules for processing each of these image categories. Now, what does it mean to have a module? These are all things we're really good at, things that we have a lot of experience with and we're actually expert at because you can't get a computer to do it. So I know you've seen this before. This is the Margaret Thatcher illusion. It was invented by Peter Thompson. This isn't Margaret Thatcher, I know that. But it's called the Margaret Thatcher illusion for historical reasons. And you know that I've manipulated one of these images, but you are looking at this image with your not expert cortex, your not face cortex. Because this doesn't qualify as an intact upright face, it doesn't get processed as a face. And now when I invert it, I hope you will be surprised at what it looks like. You are now processing it with your expert cortex. And I think that artists have figured out ways to get us to process things with our non-expert cortex. They are literally getting us to see things differently. Making something the wrong size gets us to look at it differently. Even putting something in the wrong place gets you to look at it differently. Now here you go. You've seen this, you know what I've done, but you can't process it in the same way, can you? This really is the same image. Isn't that surprising? I mean, I've seen it 100 times and it still astonishes me. All right, the last thing I want to talk about is stereopsis. So if some of you have stereopsis, 10% of otherwise normal people do not have stereopsis, so don't worry, okay? Both eyes open, blue on the right. That's stereopsis, okay? And we're going to talk about the fact that 10% of otherwise normal people do not have stereopsis. It's just geometry. You have two eyes. They're horizontally separated by a couple of inches. So if you're looking at an object, it casts images on corresponding parts of your two retinas. But things that are closer or farther away cast images on non-corresponding parts of your retina, and your visual system uses those teeny tiny differences in where the image is cast in your two retinas as part of its computation for distance and depth. So your assignment, there is an assignment here, is to go to the art museum and find a painting that's full of depth cues of shading and perspective and stuff like that. And when you stand in front of it, these other depth cues, the shading, the perspective, are telling you about the three-dimensionality that the artist was trying to convey, but your stereo is saying, no, it's flat. So close one eye. Stand in front of it, close one eye, and you will fall into the painting. But it has to fill your visual field, so you need to do this at the art museum. But stereo matching is a difficult computational problem. Now, no glasses, okay? If I tell you that blue is white to your right eye and red is white to your left eye, can you figure out what this shows? You're a pretty sophisticated audience. Simple algorithm? No, okay. Both eyes open, blue on the right, and your visual system will solve this difficult problem for you instantly. Isn't your visual system smart? Okay. Yeah. Now, some of you don't see this. Don't worry about it. If you have 4 identical images in the world, they cast 4 images on your 2 retinas, and your visual system could interpret this as being what's out there in the world. But your visual system could match the right image in your right eye with the 3rd image in your left eye, and it would correspond to exactly the same object, but at a different distance. So if you've ever misstepped when you're on an escalator, you do that because for some stupid reason, escalators have these repeating slats, and your visual system can misfuse them, which corresponds to an escalator step at a different distance than you thought it was. I think some post-impressionists have figured out ways to achieve a sense of 3-dimensionality using misfused stereo, so all these little dots can kind of misfuse in your 2 eyes to be a volume of speckly, dusty stuff. And I don't even like looking at this one. Because the leaves can misfuse in your 2 eyes and seem quite 3-dimensional. But what's weird about this one is the guy who painted it didn't have stereopsis. How do I know he didn't have stereopsis? He's cross-eyed. He's cross-eyed. He couldn't possibly have stereopsis. Stereopsis, the computations for stereopsis occur in primary visual cortex, where the world is precisely mapped onto your cortex. And if your eyes aren't pointing in the same direction, then different parts of the visual world end up in the same part of visual cortex. You can't possibly compute stereopsis that way. I got interested in the idea that artistic talent and odd depth perception might be correlated because of work that I was doing looking at equal luminant, equal value text on different colored backgrounds. So this looks kind of shimmery and weird, right? It's not quite equal luminant. I tried. I got it close. People with dyslexia. Dyslexia is a selective problem in learning to read. So people of normal intelligence with adequate education, some of them have a terrible time learning to read, and this problem persists into adulthood. Many of these people, it's called dyslexia, many of these people complain that black and white text has a shimmery, nasty quality, and they don't like looking at it, just like what equal value text looks like to me. So I did some experiments that led us to believe that there was a slight slowing or a slight timing difference in the wear system in people with dyslexia. And remember what the wear system does: motion, depth, spatial organization, and figure ground segregation. Well, what are the symptoms of dyslexia in addition to a selective problem learning to read? Well, positional information, figure ground problems, and trouble gauging distance and depth. There are similar issues in the auditory system. The auditory system may also be subdivided into a fast and a slow subdivision. The dorsal stream is actually faster than the ventral stream. I didn't mention that. So people with dyslexia often can't hear very fast auditory transitions. And phonemes like ba and da are very fast auditory transitions. So the difference between ba and da happens in about 40 milliseconds. So when I was doing this research, I was privileged to meet a number of people with dyslexia. And it was inescapable that a large majority of them were actors, computer programmers, artists, and musicians. And it's been documented that artists are overrepresented in the dyslexics are overrepresented in the artistic population. But the usual explanation is they were no good at academic subjects, so they spent all their time in the art room. But I was so impressed by how talented some of these people were that I just started thinking, maybe there's something about dyslexia that makes them bad at reading but good at music and computer programming and art. So music, sure. That makes sense because phonemes are fast auditory transitions, but music is slow. So maybe they're selectively better at slow auditory transitions. But I work on vision, so I'm not going to talk about that. How about, why would there be so many artists who are dyslexic? Well, have you ever tried to draw a chair? I can't do it. It's really hard. I don't have access to my low-level retinal images. All I have access to is the three-dimensional information that my visual system has extracted so that I'm not going to trip over this chair. And I can't flatten it again. Well, what if seeing the world as slightly flat gives a child an advantage in flattening things onto a piece of paper? Maybe he'll, as a young kid, just be good at drawing. So we entertained the idea that maybe bad depth perception is an asset for an artist. And we started looking at some famous artists. This is Chuck Close. He has anisometropia. His two lenses are different strength. He's severely dyslexic, and he says he sees the world as flat. So I told you that a lot of people have no stereopsis, and many of them because they don't have lined up eyes. So there's a clinical test for seeing if somebody could have normal stereopsis, which is to look where the light reflection is in their two eyes. See how the light reflects is in exactly the same place in that guy's two eyes? That means he could have normal stereopsis. His eyes are lined up. So here's some baseball players. You see where the light reflex is in exactly the same place in their two eyes? Okay, are you good at this yet? Okay, one baseball player had no stereopsis. See, the light reflex is centered in that eye, and it's off to the side in that eye. So Babe Ruth's eyes were not lined up. He was almost blind in one eye because of what's called amblyopia. So if your eyes are not lined up when you're a child, your brain does not want to see double. So it can suppress the input from one eye, in which case you become almost blind in that eye because the connections to the brain go away. That's called amblyopia or lazy eye. Or you can alternate which eye you look through, and that's called alternating strabismus. Babe Ruth became amblyopia. So I told you 10% of the population is stereoblind, but only 3% of the population has significantly misaligned eyes. So the other 7% are just don't have stereo for some other reason. But so we found about 100 famous artists where we could see where the eyes were lined up, and you'd expect that we would have found 2 or 3 of them that had misaligned eyes. We found like 16 right off the bat. This is Andrew Wyatt. This eye is looking at you. This eye is looking at the blackboard. His father, N.C. Wyatt, was also strabismic and was also an illustrator. Edward Hopper, light reflex is near the pupil on this eye and on the edge of the iris on this eye. Carol Walker, see the light reflex is in different places in her 2 eyes. Carol Walker works in silhouettes. How flat can you get? I don't know about the dog. Mark Chagall was cross-eyed. Frank Stella was cross-eyed. Robert Jasper Johns was cross-eyed. Robert Rauschenberg was cross-eyed and severely dyslexic. Alexander Calder, marvelous. Man Ray. Frank Lloyd Wright. Now I told you it is an acceptable clinical test to take a photograph of somebody and diagnose strabismus. It is not an acceptable clinical test to look at painting and diagnose strabismus. Could paint different times, and the eyes move several times a second. But I was at the Louvre, and there's a little tiny room that has one Rembrandt Self-Portrait on each of the walls. All that's in this room. And it was inescapable that all 4 of these self-portraits had one of his eyes deviating off to the side and the other eye looking straight ahead. Now, I know when you paint a self-portrait, you use a mirror. When you paint your right eye, you look to the right. When you paint your left eye, you look to the left. So here's a montage of me. Here I'm looking at my right eye, and here I'm looking at my left eye. And you can see that the light reflex is not quite in the same place in my 2 eyes, even though I have stereopsis. But my eyes are not nearly as deviated as Rembrandt portrays himself. So at this point, I had a pile of reproductions of Rembrandt self-portraits on my desk. And my young colleague came into my office and said, "Is it always the same eye?" And I said, "No, if it was always the same eye, I could get it published." Sometimes it's the eye on this side that deviates, and sometimes it's the eye on this side that deviates. And my young colleague, who is himself a stereoblind artist, said, "Marge, you have to separate the paintings and the etchings." So when we did this, we found in the paintings it was always the eye on this side that deviated, and in the etchings it was always the eye on this side. Etching, you scratch on a plate and you flip it over, right? So then we made a little program where we outlined the eye, and we figured out where the iris was in all of these self-portraits, and we plotted a graph. And the take-home message from this is if you can make a graph of something truly unlikely, you can get it published. This is the only thing I have ever published in the New England Journal of Medicine. And in virtually all of the paintings, it's the eye on the right that's centered, the eye on the left that deviates, except for this one, which is in Berlin, which means that either the painting in Berlin is a fake or he made it from an etching. And the etchings are systematically reversed. So he wasn't it wasn't an artistic trope. He wasn't trying to achieve some stylistic thing, because otherwise they wouldn't be systematically reversed. He was probably just drawing exactly what he saw, and he had one eye that deviated out. Now, I don't think that if you want to have someone be a good artist, you need to poke an eye out, because I'm pretty sure that the first thing they teach you in drawing one is close one eye. So here are the take-home messages. You don't really need a take-home message, but here we go. Vision is that's the key. Vision is information processing, and some of the most basic aspects of our vision are colorblind. You don't have to color inside the line, and people are different, and I hope you'll leave the stereo glasses at the rear when you leave, and I'm happy to take questions.
We do have 10-minute questions, and then we can have dinner served.
We have a question in the back here.
What breaks down the face blindness? You said there are a few cells that recognize different traits. Are those cells dead, or the interconnection or the memory of what those cells saw?
So when we first started working on face cells, it became obvious to me that there's a huge number of psychologists out there who work on face processing and study this sort of thing and do fMRI. And virtually all of them think that these modules are innate. And I am of the minority point of view, coming from the Hubel weasel, you can rewire the entire visual cortex by closing one eye point of view, that there is no way that something 6 synapses past V1 is going to be innate. So I think it's experience dependent. That's the kind of research we're doing now. And so I assume either that part of the brain doesn't respond well to experience, or the child just didn't pay any attention to faces because he had too many video games or something. I don't really know. But certainly things do go wrong with face processing. I think it's learned, but that's a minority point of view. But we have very good evidence. Yes?
Do you think that the same cells responsible for recognizing components of faces might also be why we tend to anthropomorphize objects like the front of the car?
Absolutely. Yes, we'll see a face in anything. We have learned to see faces because they're very important to us. They're ubiquitous. Look at all these faces. Yes?
Talk about the slowing of the aware system, and dyslexia possibly being advantaged, loss of stereopsis possibly being advantaged. What about impairments in color vision? Is there a particular situation that loss of one of the cones might give you an advantage as an artist? What might it do for you?
The only artist that I know, this guy that paints the English landscapes that are all blue and yellow. Constable. But I don't think it's an advantage as if someone who's going to try to make images that other people are going to look at, I don't think it's an advantage to see things differently from most people who are going to look at what you make. It might be good for camouflage, like if you get jet pilot or something. I don't think it's very good for being an artist. Got two back there. You two work it out.
Do you have any theories about why computer programmers might be overrepresented in the dyslexic population?
Because you don't read computer programs by moving your eyes a lot. You read them letter by letter by letter, practically. You don't read them fluently the way you read a novel. So that's my assumption, because if you're reading something slowly letter by letter, you're going to be much better at debugging your code. Yes?
So we know that people tend to see people from within their racial group as being more visually distinct in terms of their faces than people outside of the racial group.
Yes, the other race effect.
Has there been any work linking that to maybe the ramp-shaped contrasting being sort of experience-dependent or learned as a rule?
So yes, the other race effect, which is they all look the same to me, and I don't care what race you are, they all look the same. Whoever they are, it isn't you. It turns out you learn to see the faces you grew up with. And so I have a video somewhere that I can't find of a kid named Adam that I found, who was a white kid who grew up in Jamaica. And Jamaica is predominantly African heritage. And I asked Adam what it was like when he first came to the US. And he said in this marvelous Jamaican accent that it was terrible. He couldn't tell white people apart, especially girls he couldn't tell apart, and it became very awkward when he started dating them. That is my favorite documentation of the other race effect. But yes, it's learned. You get and there's a age. It's like language. You know, you can't learn languages very well after puberty. You can't learn to discriminate faces very well after puberty either. At least not as well as you could when you were little. So that's the other race effect. Yes. What happened to the other person up there that you beat out?
That was me.
Oh, I got both of you?
Yeah.
Okay, now you're.
How does that synesthesia?
Oh, synesthesia.
Yeah, synesthesia. How does that relate to the visual system?
So the kinds of things that people often cross. So synesthesia is otherwise normal people have sensory processing that crosses modalities. So the most common kind, I think, is you look at letters and see colors. Real projector synesthetes actually see the colors kind of glowing around the letters and numbers. You can have music color, touch, sound. And usually the connections are between areas that are very near each other. So the numbered letter area is very near the color area. And I didn't even know that I had synesthesia until I heard a lecture by David Eagleman, where he wrote the Wednesday in what turned out to be, for me, quite the wrong color. And it can be as mild as just having a conviction that the days of the week have a color associated with them. So there are all kinds of ranges of this. Ramachandran, whose first name I can never pronounce, says that it's part of creativity to be able to make connections between disparate things, and he likens it to metaphor. So one time I was giving a lecture at Pixar, which is a place full of creative people. So somebody asked this question, and I said, does anybody in the audience have synesthesia? And of course, nobody answered, right? Nobody was going to admit they had synesthesia. But afterwards, there was like 10 people who came up to me. 7 of them were talking about numbers and colors and stuff like that, and there were 3 of them standing there arguing about Rachmaninoff and the key of G. And it turned out that they weren't sure that associating colors with notes was a synesthesia or not, because it was so real to them that they thought that everybody did this. Yes?
If synesthesia usually involves areas of the brain that are close together, or are kind of mechanistic explanations that are different when you have, say, auditory and visual synesthesia or areas that are
Oh, I don't know about that. I discovered a kind of synesthesia. So I'm from the 60s, okay? You know, with the hippies and stuff like that. And I realized that it was very popular for people to have auras. Do you know what that is? People could see aura, and I realized that that's a face color. synesthesia, it's very common for people to see color associated with faces. But no, I don't know how you can cross modalities. I guess higher up in the temporal lobe, they get pretty close together. And I think they're probably going to be high-level synesthesia, but I don't know anything about the auditory system. Can't you tell? Yes?
What do you think about the growing field of neuroaesthetics? And do you think dry science is ever going to be like sufficient to explain what we
We don't understand reward. You know, we're still at the level of dopamine neurons firing and stuff. Aesthetics is so far beyond that. I don't know, yeah. way beyond. So people like to fuss about neuroaesthetics, but I regard it as kind of untouchable. We'll talk about what artists do because I can see what they've accomplished, but why we like it and whether it's great, I just count on art history books to tell me. And if an art history book says it's important, I'll look at it and think about it. Yes, way into that.
How does vision differ between different types of primates? And like what would a lemur see out of those like different optical illusions you showed us or something?
So the most noticeable thing is that among primates, only old world primates, so monkeys out of Africa, like us, monkeys and great apes, we're the only ones with trichromacy. So all the little monkeys that we have in South America and stuff like that, they're red-green colored ones. But mostly their vision is like ours otherwise. Yes?
What about someone who's albino?
Oh, they have a optic chiasm crossing problem, so they're essentially cross-eyed. So I think, and they also have low acuity because of the lack of, so we have really high acuity because the light comes into our retina and then it gets absorbed by our retinal pigment epithelium. But you know how cat's eyes glow at night? They're specialized so that the light comes in and then bounces off and comes back, and so they see the light, we have 2 chances to catch it, but it means they have much lower acuity. And so I think albinos have many issues with acuity because they don't catch the light and it comes back out like cats.
All right, let's do one last question, and then we'll take it out to dinner, and you guys can definitely, like, you know, go up to Dr. Livingstone and ask her questions. It's gonna be good. Go for it.
All right, so you know when the lights are out?
All right, when the lights are out, and then you turn the lights back on,
I know, I'm
like
sorry.
in the presentation. Okay, like how come it hurts a little bit when the lights come on?
I don't know, I think you just notice it when you people. And it doesn't hurt, well, it's a reflex,
But I
you
mean,
don't want that much light.
Like if a flashlight's like flashing right into your eye, like the lights are up for like 5 minutes and then the flashlight comes right into your eye, it hurts a little bit.
Yeah.
Like, is that like my cornea burning or something? Or is that
No, but it's a series of reflexes designed to keep too much light from coming into your eye suddenly, because too much light, if it were like the sun, would burn your retina. It's just protective. Pain is for protection.
Great. Well, thank you so much. Well, as Jen mentioned, there's dinner right